Hello, it's Dr. Armand, again bringing you another exciting lecture in general chemistry. Today we'll be focusing on three main things, or two main things. We'll be focusing on hybridization, so what type of orbitals overlap to form these bonds between atoms. We'll be looking at bond enthalpy. So based on the energy it takes to break a bond, you can calculate delta H of a reaction. So those are the two important topics we'll be looking at today. So sit back, relax, and enjoy the show. And so this is the fifth part in this lecture that we've been going over through chapters 9 through 11 involving Lewis structures, geometry, and now, or polarity, and now hybridization. And so before we actually get into hybridization, there are two theories explaining how bonds form between, or two simple theories explaining how bonds form between two atoms. And one of them is valence bond theory, which is denoted as the number of lone electrons dictates the number of bonds. And then there's hybrid orbital theory, which does a better job. And so first we're going to talk about valence bond model or atomic orbital model. And this is a way we can describe what a covalent bond is. So there are two types of descriptions we're going to talk about. This is one of them, atomic orbital or valence bond model, and the other one is hybrid orbitals. And so now let's take a look at the hydrogen atom. Hydrogen atom has one lone electron in the 1s orbital, as we see here. One second. Oh. There we go. And so when H is in a stable molecule, it can accommodate that extra shared electron from another atom. So for example, if we have the H2 molecule, well, each hydrogen has one electron and they can share the other electron. And this is why hydrogen forms a single bond. It has one lone electron, it can only accommodate one more electron in its orbital. So when you share, for example, HF, the hydrogen is sharing one electron with another hydrogen, so each hydrogen has two electrons. And so valence bond model says that since the hydrogen atom has one lone electron, it can form one bond. So if, for example, we did HF, the same thing. Hydrogen has one lone electron, it can form one bond. Just like fluorine has one lone electron, it can form one bond. So it does a good job of explaining how hydrogen can form one bond. The same thing with fluorine. So fluorine has one lone electron, shown here. So according to atomic orbital valence bond model, it can form a single bond because it can accommodate one more electron in its half-filled 2p atomic orbital. So in the HF molecule, like I've shown here, fluorine can accommodate that extra shared electron from hydrogen. So it does a good job with the halogens and explaining why halogens like to have single bonds in molecules. So in general, an atom needs an unpaired electron to form a covalent bond according to this model. So according to valence bond model or atomic orbital model, you need at least one unpaired electron to form a bond. And so this is true for hydrogens and halogens. So each one of those has one lone electron. It can form one bond with another atom. Now if we look at boron, boron has one lone electron. So according to this model, it should form it should only form one single bond. However, this is not correct because we've seen some compounds where boron forms 3 bonds. For example, BF3. So in BF3, boron forms 3 single bonds, but this model says it can only form 1 bond. Well, that can't be right. I mean, if it forms 3 bonds and this model says it forms 1 bond, obviously this model doesn't work for boron. We go to carbon. It says carbon only has 2 single bonds, so according to this valence bond model, it can only form 2 bonds. But this is not right because we know carbon likes to form up to 4 bonds. For example, CCl4, carbon has 4 bonds. So obviously it doesn't work for carbon. Now if we look at sulfur, sulfur only has 2 lone electrons. So according to this valence bond model, it can only form 2 bonds. Well, we know that's not correct either because sulfur can form up to 6 bonds. So obviously for elements other than hydrogen and halogens, it doesn't do a good job of explaining the number of bonds these different elements can form. So what we have to do is we have to introduce what's called a hybrid orbital. And so this is the result of mixing atomic orbitals to form hybrid orbitals. It's kind of like that movie back in the day, Underworld, where you had vampires and werewolves, or lichens, and then if you cross them or mix them, you get this new hybrid vampire werewolf. The same thing here. We have atomic orbitals like an s and a p orbital. You mix them, you get characteristics of both. So the same thing is done here. So we're going to talk about hybrid orbital theory. So this explains why certain elements can form 3 bonds while other elements can form 4, 5, or 6 bonds. So we'll start with something simple. I'm just going to show you how these hybrid orbitals are derived. You know, if you don't remember it, it's not the end of the world, but at least you can see where the notation comes from. So here we have beryllium difluoride. Beryllium's outer electron configuration is 2s2, so it has a completely filled 2s orbital. It needs to accommodate the extra 2 electrons shared by fluorine. So you can't just stuff them into the 2s orbital because it's already filled. So what we do is we take the 2s orbital, atomic orbital, and one 2p orbital, and now we get what's called 2 sp hybridized orbitals. So now the beryllium is what we call sp hybridized. So again, we take our atomic orbitals. So on this side, they're called atomic orbitals. And then we take one s atomic orbital, one 2s atomic orbital, and one 2p atomic orbital, and we get 2 sp hybridized orbitals. And so now we can accommodate the extra 2 electrons by fluorine. And these orbitals are degenerate, meaning they're the same energy. So orbitals so one is not higher than the other. And so that's how beryllium can accommodate the extra 2 electrons from fluorine. We say beryllium is sp hybridized. And it makes sense because we have 2 bonds, just like beryllium can form 2 bonds. Next we have boron trifluoride. So boron's outer orbitals are 2s2, 2p1. Each fluorine shares 1 electron, so boron has to accommodate the extra 3 electrons from the fluorine, but it only has a 2s and a 2p orbital. So what we're going to do is you take one 2s orbital and two 2p orbitals, and we're going to form 3 sp2 hybridized orbitals. So again, on the left side are atomic orbitals, on the right side are the hybrid orbitals. So now we have these 3 degenerate orbitals, because remember, the atomic orbitals are not degenerate. 2p is higher in energy than 2s. But when we take these and mix them, now we get 3 degenerate orbitals, and this is an sp2 hybridized orbital. So there are 3 hybrid orbitals. So if you look at it, s plus 2p gives you 3. So there's 3 degenerate orbitals, whereas s plus p gives you 2. And so we would say boron is sp2 hybridized. Next we have silicon tetrafluoride. Each silicon, or excuse me, silicon has 3s2, 3p2 outer orbital configuration. Each fluorine, there should be a fluorine here, shares 1 electron. So silicon has to accommodate the extra 4 electrons from fluorines. So what do? That's right, we take 1s and 3p orbitals, and we get 4 sp3 hybridized orbitals. So now silicon can accommodate the extra 4 electrons being shared by the fluorine atoms. And so we say that silicon is sp3 hybridized. Now, row 2 elements or period 2, I should say period 2 elements can only be either sp, sp2, or sp3 hybridized. So if you have a row 2 element as a central atom, the maximum hybridization it can be is sp3. So it's either going to be sp, sp2, sp3 hybrid orbitals for your period 2 elements. So things like boron, carbon, nitrogen, oxygen, fluorine, all of those maximum sp3 hybridized. Now the other 2 types of hybrid orbitals, you'll see why period 2 elements can't be those types of hybrid orbitals. So now let's look at phosphorus pentafluoride. So phosphorus has a partially filled p orbital, or a half filled p orbital, and completely filled s orbital, but it needs to accommodate the 5 shared electrons from the fluorine. So obviously it won't fit in the 3p orbital because it only can fit 3. But there's no other p orbital. There's only 3 of them. There's not a 4th one. So what do? We take 1s, 3p, and 1d orbital to form 5 sp3d hybridized orbitals. So again, s is 1, p is 3, d is 1, that adds up to 5. And so this is why row 2 elements can't behave as, or can't have this type of hybridization, because row 2 elements do not have a d orbital. Because this is the second energy level, there's no d orbital in the second energy level. So therefore, row period 2 elements cannot be sp3d hybridized. So here we would say phosphorus And then we have sulfur hexafluoride. So sulfur is 3s2, 3p4. So we only have 2 slots for sulfur to accommodate any extra electrons, but we have 6 electrons we have to share. So what do? We take 1s, 3p, and 2 d orbitals, and we form 6 sp3d2 hybridized orbitals. And so now we can accommodate these 6 extra electrons being shared by the fluorine atom. And so we would say sulfur is sp3d2 hybridized. And notice that sp3d2 adds up to 6. So when sulfur has 6 electron pairs around it, it's going to be sp3d2 hybridized. But for example, sp3d adds up to 5, which means when the central atom has 5 electron pairs around it, it's going to be sp3d hybridized. Let me go back. And so now we can kind of summarize this based on the number of electron pairs around the central atom or based on its electron geometry. So for example, if something has 2 electron pairs around the central atom, it's going to be sp hybridized. Or you can remember if it has linear electron geometry, this should be electron geometry, then it's going to be sp hybridized. This is, we mean electronic geometry. Number of electron pairs around central atom. And we'll show some examples of these in just a moment. So 3 electron pairs, sp2. Remember 1s and 2p adds up to 3. 4 electron pairs, sp3, tetrahedral. 5 electron pairs, sp3d, or you can, if it's trigonal bipyramidal. 6 electron pairs, sp3d2, octahedral. And so remember, for row 2 elements, you can't go beyond sp3. So now we're going to look at some examples determining the hybridization of the central atom. Again, this is only for the central atom. So again, as always, it's very important that you draw the correct Lewis structure so that you get the correct number of electron pairs to determine the hybridization. So here we have the Lewis structure of SF2. And you see that we have 1, 2, 3, 4 electron pairs. So 4 electron pairs means sulfur is sp3 hybridized. Now, a trick to this is you could count like this. You could go, if you remember, S has 1, so you could go S, P, P, P. So then it's like, that's like a little shortcut to determine that this is sp3 hybridized. Just remember, S has 1, P has 3, and then D has 2. So this sulfur is sp3 hybridized because it has 4 electron pairs, 4 electron pairs, and it is tetrahedral electron geometry. Now, if I draw another one below it, just for comparison, let's say we have silicon dioxide. And so silicon dioxide, if we look, now we count double bonds as one electron pair. So this is 1, this is 2. So again, double and triple bonds count as one electron pair. So here's silicon is sp hybridized. And so again, the shortcut, you could go SP. That's a shortcut. And so again, double and triple bonds, let me write it over here. Double and triple bonds around the central atom count as one electron pair. Now we have IF3. Let's count the number of electron pairs. So we have 1, 2, 3, 4, 5. And so this means that iodine is sp3d hybridized. If we were to use a shortcut, we could go S P P P D, and that's where we get the shortcut to know it's sp3d hybridized. Then lastly, we have xenon tetrafluoride. So if we count the pairs of electrons around the central atom, we have 1, 2, 3, 4, 5, 6. So we would say that xenon is sp3d2 hybridized. If we use our little shortcut, we could go S P P P D. This is like the shortcut if you can't remember electron pairs with the hybridization. So this is sp3d2 hybridized, and xenon is octahedral electronic geometry. And so that's how you identify hybridization. You draw the Lewis structure, determine the number of lone pairs of electrons around the central atom, and then from there, based on the number of pairs of electrons, you can determine the hybridization. Just remember that double and triple bonds count as one electron pair. Now the next slide is when we have multiple central atoms, how do we determine the hybridization? So for example, in this molecule, we have carbon, nitrogens, and oxygens, and we want to know what's the hybridization of nitrogen atom next with the X next to it. And what you have to remember here is that nitrogen, carbon, oxygen are period 2 elements. So the hybridization can only be sp, sp2, or sp3. That's it, because these are row 2 elements. So let's look at this first nitrogen here with the X. Let's count the number of electron pairs. So this is a double bond, counts as 1. So this is 1, 2, 3. So we have 3 electron pairs. So that means it's sp2 hybridized. So if we do our shortcut, we say this is sp2. Now if we look at the other nitrogen on the other side, here we have 1, 2, 3, 4. So we have 4 electron pairs. This means it's sp3 hybridized. If we do our little shortcut, we see we have sp p p. And so that's how you determine the hybridization for those elements that are in compounds with more than one central atom. So now the last topic in this chapter, or the last topic that we'll be talking about in this lecture is bond enthalpy. So this is the amount of energy that it takes to break a particular bond when you have 1 mole of gaseous molecules. And so as you can see, HH bond is 436 kilojoules, whereas the chloride-chloride bond is 243. Now, for example, the reason that the chlorine bond is easier to break than the hydrogen bond, the HH single bond, is because the chlorine atoms are further apart, so it's easier to break. And that's why chlorine bond is easier to break than a hydrogen bond. And so the further apart atoms are, the easier it is to break those atoms. That's why when we look at a chlorine-chlorine single bond, very low energy, but when we go to an oxygen-oxygen double bond, the energy increases because now you have more electrons between the 2 atoms, so it takes more energy to break them. And then a nitrogen-nitrogen triple bond is an extremely strong bond, so it takes a lot of energy to break it. And so the more energy it takes to break a bond, the more stable the bond is. And so here, when you're breaking a bond from a molecule, it's going to be endothermic. But when we have a chemical reaction, when it's an exothermic reaction, this means that the bonds of products are more stable than bonds of reactants. So for example, when we make water or steam from hydrogen gas and oxygen gas, since it's exothermic, it means the bonds of the products are more stable than the bonds of the reactants. Likewise, endothermic means that bonds of reactants are more stable than bonds of products. So when we break a nitrogen-nitrogen bond, those nitrogen atoms are very unstable. That's why it takes a lot of energy to break them. And so this is what you can interpret from a chemical reaction if it's endo or exothermic. If it's exothermic, the products are more stable than the reactants. If it's endothermic, the reactants are more stable than the products. And so there's a few things we can learn about trying to determine which bonds are stronger than other bonds. And so the first category is when we have the same atom but different type of bonds. So here we have nitrogen-nitrogen type nitrogen bonds, and we see we have a single, double, and triple. So if the same two atoms are being compared with just different types of bonds, the triple bond would be the strongest, followed by the double bond, and then the single bond is the weakest. The same thing when we have CO, the CO bond, single bond, CO double bond, and CO triple bond. The triple bond has the strongest amount or the largest amount of energy to break it. Now you'll notice that the carbon-oxygen triple bond is more energetic than the nitrogen-nitrogen triple bond. And this is because the CO bond is polar and the NN bond is nonpolar. And that leads us into the second category when we're comparing different types of the same bond. And so again, when we're comparing the same type of bond, just different types of atoms, the one with a greater difference in electronegativity is the stronger bond. So for example, here we have carbon sulfur single bond, carbon nitrogen, carbon oxygen, carbon fluorine. The carbon fluorine is the strongest because it's the most polar bond out of these. And carbon sulfide is the weakest because it's actually nonpolar. It's the least polar bond out of this. So when you're comparing the same type of bond but just different atoms, the one with the greatest difference in electronegativity is the one with the largest bond energy or the strongest bond. So like for here, when we look at the double bonds, again, the carbon sulfur double bond is the weakest because again, carbon sulfur bond is nonpolar, but carbon oxygen bond is the strongest because it's the most polar bond out of these three. And even the carbon oxygen bond is stronger, the double bond is stronger than the nitrogen nitrogen double bond because again, carbon oxygen is polar, nitrogen nitrogen is nonpolar. And so that's how you can rank bonds based on whether they have their difference in electronegativity. Now here you don't need electronegativity values, you just need to look at the trends in electronegativity because we still have the same carbon on all of the bonds. Now you don't have to memorize these bond energies. There's a table in your book. Also, there's if you have it on a quiz question or an exam question, they're going to be given to you. So you don't have to memorize any of these. But just notice here that the oxygen hydrogen single bond is stronger than the oxygen carbon single bond, for example. And that's because oxygen hydrogen's greater electronegativity difference than carbon oxygen. So it takes more energy to break it. So here we have this set of bonds, and we want to know which of the following bonds would have the highest bond energy. And since they're all single bonds, the one with the highest energy would be the one with the greatest difference in electronegativity. And so if we look here, well, obviously it's not going to be the carbon-carbon bond because they're the same. It's going to have zero electronegativity. 1 second. I got to plug in my computer before it does. There we go. And then obviously it wouldn't be carbon hydrogen because we said that's the most common type of heteronuclear nonpolar bond. So we narrowed it down to carbon oxygen, carbon fluorine, carbon chlorine, and carbon iodine. So you got to see which one of these, oxygen, fluorine, chlorine, or iodine, has the greatest electronegativity. And as you should remember, the most electronegative element on the periodic table is fluorine. So the carbon-fluorine bond would be the strongest bond out of all of these. The next strongest bond would be carbon-oxygen, because oxygen is the second most electronegative element on the periodic table. So now sometimes we may want to determine the bond energies. So let's say we have two homonuclear diatomic H2 and I2, and we want to determine what the bond energy of HI would be. And so we would think it would be the average between the HH and the II bond. So let's see if that's true. Let's look at some of these homonuclear diatomic species and the bonds they produce, and see if this is the mean or the average between the individual bond energies of the two homonuclear diatomic molecules. And so here you look at the HF, 436 is the HH bond, 159 is the FF bond, so the average is 298. But what we observe is 570. For HCl, the average is 339, but what we observe is 432. For HBr, the average is 315. What we observe is 366. For HI, the average is 294. What we observe is 298. And so you can see the only one that is close to the average is HI. The other ones are above the average between the two individual bonds of the homonuclear diatomic molecules. So only HI is close, the experimental value is close to the average value. And so you see the difference in the expected, which is the average, and the measured decreases as we go from HF to HCl to HBr. And the reason it decreases is because as we go down, bonds are less polar. So this average only works when you have a non-polar bond. And so again, what's happening as we go from HF to HCl to HBr to HI is that we're decreasing the polarity, where HI is actually a non-polar bond or close to it. So the less polar the bond is, the more likely that the expected bond energy is going to be similar to the measured bond energy. And that's why HI is very close to its expected bond energy, because HI is a non-polar bond. So again, why are heteronuclear bonds, some are stronger than expected? This is because when it's a symmetrical bond, and we're talking about the electrons in the bond are shared equally, it's a symmetrical bond. These are non-polar bonds. That's what we mean by symmetrical bonds. nonpolar bonds. So they sit equally from one another, then you can determine the mean of those two different types of bonds and then get the average of the heteronuclear bond. Because if this is lithium, lithium, and then you have, for example, these two lithiums have the same energy, then you can determine this is nonpolar because it's lithium, lithium bond. So asymmetrical bonds is when the electrons are not shared equally between two atoms, and this is referred to as a polar bond. And so in a polar bond, electrons sit closer to one side than the other, and this is why you have a stronger bond in a polar bond versus a nonpolar bond. And that's why heteronuclear polar bonds, bond energies, are usually much greater than the average of the two homonuclear bonds that make up the heteronuclear bond. And so in summary, when you have polar bonds, since the electrons are held more tightly by the atom's bond, it's much harder to break, so therefore the bond energy is going to be greater than the average of the two bonds. So for example, if we have an HF bond, okay, the bond energy of HF bond would be greater than the average of the average between the HH and FF bond energies. And it's because the HF bond is a polar bond, HF. And the more polar the bond is, the higher it will be above the average of the individual homonuclear bonds. But for example, if we had, let's see, yeah. And so that's what we mean by why some heteronuclear bonds are stronger, much stronger than expected, is because there are higher electronegativity difference in the atom, so electrons are pulled to one side of the bond more than the other, so it becomes much harder to break. And for example, the HF bond, the bond energy of the HF bond would be greater than the average, actually a lot greater than the average between HH and FF bond energies. And I know I spelled energies wrong. Let me correct it. So now we can use bond energies to calculate the delta H of reaction. This is another way to calculate delta H of reaction. So we take the sum of the reactant bonds, the energies of the reactant bonds broken, minus the sum of the energies of the bonds formed in the products. That difference will tell us delta H of reaction. So here we have H2 plus F2 gives us 2HF. So you look up the bond energy. So an HH bond is 432 kilojoules, and FF bond is 159. So the total energy broken by the reactants is 591. Since we have two HF bonds, we multiply 565 by 2, we get 1130. Now it's going to be here for bond energies, this reactants minus products, we get negative 539. And this tells us that HF bond is more stable than the reactants because it's exothermic. And that's how you calculate the delta H from bond enthalpies. Look at another example. So here we have Cl2 plus F2 gives us 2Cl3. Again, we need a balanced chemical equation. So what you need to do is draw the Lewis structures of each reactant and product to determine the types and number and types of bonds that you have. So we're going to have one Cl-Cl bond, 3 F bonds, and then we have 2 molecules of ClF3. That means we're going to have 6 ClF3 bonds. So the sum of the bond energies of reactants equals 243 plus 3 times 159. That's 402. Then we do the same thing for the products. It would be 6 times 193. $1,160. So now delta H, 402 minus 1160. Be negative 758 kilojoules. And so that's the delta H of this reaction. Again, it's very important that you draw the Lewis structures of each reactant and product to see the types and number of bonds that you have. So this is exothermic, meaning the products are more stable than the reactants. Look at one more example. Here we have a combustion reaction. Again, the bond enthalpies for the individual bonds are this. We need to draw out the Lewis structures of all the reactants and products. So it looks something like this. So the sum of bond energy of reactants, we have 2 carbon-carbon double bonds, so 2 times 611 plus 4 CH bonds, 415, plus 3 double bond oxygens, 498. We get 4,380 kilojoules. We do the same thing for products, so sum of bond energy of products. We have 4 carbon-oxygen double bonds plus 4 oxygen-hydrogen single bonds. Get 4,820 kilojoules. And then the delta H, 4,380 minus 4,820 equals negative 440 kilojoules. And that tells us that the reaction is exothermic and the products are more stable than the reactants. So that concludes today's lecture on hybridization and bond enthalpy. I hope you enjoyed today's lecture. If you liked the lecture or you learned something new, make sure you hit the like button. And until next time, Dr. Armand signing off.